Off last week as we had gone through all of the important scientific discoveries leading up to the formation of quantum mechanics by Schrodinger, and we kind of left it as that he has this big, ugly equation that he calls a wave function that's got lots of mathematical garbage in it that we don't ever want to know. And what we're going to take home from it is we're going to look at how it describes where the electrons are based on a few simple numbers that are used to describe them. I do want to review just briefly and point out that one of the things that we're aiming to explain is the idea of those line spectra. And so you can see from the picture here, the idea is that we have a tube full of hydrogen gas, and we pass that through a prism, and instead of getting a rainbow like we would normally for white light, we only get a few specific lines for them, and that's why they're called line spectra, because there's only a couple lines of color. And we talked about how Bohr, this is line spectra for all the other different elements. And we talked about how Bohr had so this is sort of our Bohr model, talked about electron orbitals. And what he basically is saying is that if an electron is in that innermost orbital and it absorbs some energy, it can go up in energy, it can be pulled away from the nucleus, but that when it goes back to the nucleus, it emits light. So here's light emission. And this would be an example of light absorption. And so we can draw that Bohr model and we can show all those levels, but realize that what it's really saying in here is that that innermost orbital we can call, say, n equals 1. The next one we're just going to call the number 2 orbital. The next one out is the number 3 orbital. And that we can translate from this sort of picture of the atom model to just drawing it how we have it at the right-hand side, where we just draw the energy levels kind of in a scale where, this is that n equals 1 level, that's that n equals 2 level, and that's that n equals 3 level. And what we find is that that n equals 1 level is sometimes considered the ground state. It's considered the, where it normally resides. And that any state that is not normal, meaning that's higher in energy, or where that electron is further out from the nucleus than it should be, are called excited states. And so the idea is that the light emitted from hydrogen is due to the transitions from an excited state of an electron to a ground state. And so if we kind of go back a couple pages, we might see that, specifically this line is the transition from the 3rd level back to the 1st level. And that this emission is from, say, the 4th level, and it doesn't have to always go back to 1, it might go back to only the 2nd level. And so the idea is that how far the electrons are from the nucleus kind of determines what color of light is going to come out from that atom. And so what we're going to do is we're going to take those and we're going to expand those ideas a little bit more, but always fall back to that Bohr model. Even though it's not perfect, even though it's not really exact orbitals like that, even though we know it's supposed to be a wave instead of like a particle, even though we know that we're supposed to talk about things in terms of probabilities, worst case scenario, the Bohr model gets you like 95% of the way to where you want to go for most things. And so it's a good fallback position. And this is just, I will of course print these all out for you guys at some point. I just forgot to last night. Well, two things that are, the major thing that's wrong with it is that it doesn't work for more than one electron. The second thing that's kind of wrong with it is there's no fundamental reason why it has to be quantized like that. And it's not exactly like it's wrong, it's just that having a model that predicts something with no reason why it would predict that isn't a very good model. Right. And it shows that there's still some underlying science or ideas that you have to get at. Now we're not going to, like I said, we're going to ignore the ugly, nasty quantum mechanics that gives us better answers to everything. But, which is why I say we can fall back to the Bohr model, but we shouldn't always use it. Because one of the first things we're going to find is that not all orbits are circular. So we can have different shaped orbitals. And so 99 times out of 100 when I draw a model of the atom, I'm still going to draw it just using the circular orbitals because it's pictorially easier. I'll usually draw one more orbital of the other odd-shaped ones just as a reminder that it's there. So what does what mean? Well, that's just showing that that's the light emitted. I have no idea. I mean, seriously, I didn't draw the balls. I didn't even I think it's just supposed to be the color of light.
So he just like came up with that. He didn't even really explain why.
Correct. And I mean, part of the, like I said, for 99 times out of 100, maybe in this class for sure, the Bohr model really gets everything that we really need to know. We don't really have to worry so much about the idea of waves. One of the reasons I want to, talk about the waves in that de Broglie model is that it does start to get you into that idea of, yeah, we might picture it this way, but we have to realize that that's not exactly how it is, and that if we want to talk about more complicated stuff, or we want to explain more things better, then we have to kind of step it up a notch. So this is sort of that de Broglie model, right? And he's the guy that said electrons can be waves or particles, I should say. Waves and particles. And again, I'll print these off. I just forgot to. And so what he's basically saying is that, you can have an integral number of waves around an electron, and that's what defines the size or the shape of an orbital. And also the fact that we can describe them as waves, when we start talking about quantum mechanics, we'll find that, we have to, with waves, we can have things like constructive interference and destructive interference that gives us a lot of what really ends up happening around it. And so notice that, things like 3.3 are forbidden. You can't have an orbital that's not 3 and not 4. You can't have anything in between. So there should be no electron density, or there should be no electrons between the orbitals. And this is that fancy picture I tried to draw where here it doesn't line up, and here it lines up perfectly, so it's allowed. And that's just one of the features of waves, that they have wavelengths, and that only integral number of wavelengths can fit in between any 2 points. It's kind of like I had said before, strumming a string on a guitar. And then that's where it's getting into the new ugly stuff. So we'll switch back to a blank slideshow, hopefully. Oh, good, I managed to pick one. So the idea is that we have what is called the Schroedinger Equation. And he used the variable psi to stand for the wave function. And what a wave function is it's simply the mathematical description of the wave. And it's equal to a lot of ugly math. Therefore, we skip it. And instead, we're going to go to what's called a summary of it.
What is that fork thing?
That's the Greek letter psi. And don't worry about it. It's not on the test. So what it's saying is it's just like saying x equals 5. So what he's saying is that psi, that's what he's going to call a wave, is equal to a bunch of ugly math. And we're going to try to simplify it down to x equals 5. We're not going to get quite to x equals 5, but hopefully we can simplify it down enough. And so what we can do is we can summarize his findings by realizing that there are 4 quantum numbers. And all the word quantum means is that they're quantized, or that there's only certain allowable values. And so what we're going to describe for each number is the allowed value, or well, we're going to give the name and symbol, I guess. And so what you're going to be held responsible for is the name and symbol. You should know the allowed values. And you should know what about an electron it describes. Now, also realize that in this lecture, we're going to approach it from the nitty-gritty math side of the quantum mechanics, going through all the numbers and what that all describes. And then at the tail end, what we'll do is we'll say, okay, all of this stuff is neatly summarized in the periodic table, plus a few other things that you can remember. So if you have a periodic table, for instance, which you are always allowed on these tests, about 50% of what we're going to talk about today is simply going to be derivable from the periodic table. But until you describe the mathematics of it, approaching it from the periodic table end is kind of difficult. And so realize that this is a little bit of a circular lecture, and that we have to pick some point to start, but that all the topics are going to kind of relate back to that initial starting point. The other thing we're going to do is we're going to draw you lots of sketches and pictures and diagrams. And in the end, the one that makes sense to you is the one that's going to give you that aha moment. That's why I put so many different pictures out. And so hopefully one of the 3 or 4 different ways to picture all this allows you that little aha moment. And then, long story short, at the very, very end, I'll be very clear what stuff is going to show up on the test. And if you get all the background material, it makes studying for the test and understanding what's going on easier. But, I hate to tell it to you, worst case scenario, you can just memorize all this, some of the garbage. You can just memorize what values are allowed. You don't have to understand why they're allowed or not allowed. So, memorization can get you pretty far, especially kind of in a class like this. But hopefully we can throw that understanding in there for you. Okay, so the first quantum number is called the principal quantum number. I think it's actually principal like this. I always have to laugh at some of the spelling mistakes in my notes. And it's given the symbol of kind of like a script n. And the allowed values are, n can be any number, 1, 2, 3, all the way up to infinity technically, where these are representing integers. So the idea is it's quantized, meaning you can't have 1.5, you can't have 0.37, you can't have 8.2. You have to pick 1, 2, 3, 4, all the way up to whatever kind of number we get to.
Integers or whole numbers? So it can be negative?
Technically, you're right, whole numbers, we should say that. Actually, it's not even the whole numbers, it's really the counting numbers. Because the whole numbers include 0, right? And we can't have a 0 for this quantum number. So heck, we'll even put that out. This is the counting numbers.
Oh, that's infinity, not 2, 0.
Yes, that's, excuse me, the infinity symbol. No negatives, just 1, 2, 3, 4. Pretend like you're counting on your fingers. Now, of course, if you're a computer scientist, you probably count from 0, but there's none of you in here, right? No? Okay, what this is really describing is the size of an atomic orbital. Or sometimes we call that a shell. And so what it's really saying is if we look at it exactly like the Bohr model, there's the n equals 1 shell. Then, of course, the n equals 2 shell is further out. The n equals 3 shell is further out, and you can keep going on and on forever. The n equals 4 shell. So it's simply telling us how far the electron is from the nucleus. I usually think about this quantum number as talking about, so what are those Russian dolls that nest inside each other? Nesting dolls? Hey, wow, what an awesome name. Yeah, nesting dolls.
Simple, but for those who can say matryoshka.
Okay, say it one more time so we have it on tape.
Matryoshka.
Yeah, matroshka. So it's like matroshka. And in my class next year, I won't remember it, but my class next year will be like, wow. Anyway, it's like nesting dolls. Each orbital is slightly bigger and bigger and bigger. So that one I think is pretty easy to understand. It doesn't give us too many problems. The next one gets a little weird. It's called the angular momentum quantum number.
Yeah.
The second one.
Yep. It's given the symbol of a script L. And what it describes, or what values it's allowed to have is 0, 1, all the way up to n minus 1, where, see, this is the principal quantum number. So the idea is that the L quantum number depends on the previous number. And what we're going to find is the next number depends on the previous number before it. So they're kind of like the numbers are dependent on each other. So what I mean by example is, for instance, if n equals 1, what value can L have? Just 0. Because it can't be 1 because it can only go up to n minus 1, right? So another way to say that is L has to be less than n, right? That's another way to say it. Or if n equals 2, what values are allowed? I can have L equals 0, but now I can also have L equals 1. And if I go to n equals 3, I'm allowed to have L equals 0, L equals 1, L equals 2, and so on. Does that kind of make sense?
Yeah.
Okay. So each of the L values describes the shape of an orbital. And so that's where I was saying that they're not all circles, basically. Meaning we get more complicated shapes when we go to talk to them, or talk about them. And there's also another abstraction. Each value is given
Down, yeah, you got L equals 0, 1, 2, 1.
So the idea is that L always has to be less than n, but it can be any of the integers less than n starting at 0.
Oh.
And I really shouldn't say integers, I should say whole numbers, right?
Okay.
So if it's 3, that means I can have 1, 2, 0, 1, or 2, but I can't have 3 because then they'd be the same. It always has to be less than it.
So it wouldn't be n minus 1? It would just be...
Well, it is n minus 1, because if n is 3, then L... Oh, it can be any value up to that. I see what you're saying. No, it's not just n minus 1. It's all the values up to it. And this is what is going to give the pattern that we're going to be able to pick up on eventually. So each value is given an associated letter. So for instance, if you have L equals 0, we're going to call that an s orbital. If L equals 1, we're going to call those p orbitals. If L equals 2, it's called a d orbital. If L equals 3, that's an f orbital. And then, honestly, we never go beyond f orbitals. It is possible to have other lettered orbitals. They just start going, after f, they go g and stuff, but we never have to use them. In fact, we're going to try to stick to this about 90% of the time, and maybe we'll talk about d orbitals 10% of the time. And we really don't care about the f orbitals in this class. We don't even want to care about the d orbitals, but they're there, so we should at least talk about them. And the letters S, P, D, and F really stand for they're really lost in antiquity in that, S stands for the strong lines, the lines that are very bright in the spectrum. P stands for the principal transitions, which means nothing. This is all coming from the line spectrum notation, and D stands for the lines that are more diffuse, that aren't as bright. And so, we don't have to worry about where the S, P, and D, and F come from. We just kind of have to associate in our head that we're going to have S orbitals, P orbitals, D orbitals, and F orbitals. Then we talked about shapes. So if I have an L equals 0 orbital, that's what we're going to call an S orbital. And these are really just spheres. So here's a 1s orbital, where n, that's the principal quantum number, and the s is telling us that L quantum number. So that's our n, that's our angular momentum, and that's our L quantum number. And then, of course, we can have a bigger orbital, and that's our 2s orbital. Right, so what we're saying is that we can describe the orbitals by the quantum number, the principal one, which is telling us how far out it is, right? And then the s is going to tell us the shape that I draw. So a 1s orbital is small, a 2s orbital is bigger, a 3s orbital is further out. And so s orbitals are just spheres. Now here's the other thing. Remember, this is supposed to be 3 dimensions, right? So even though we talk about it being, or draw it as a circular, remember this is a sphere. In fact, Jay, since you're sitting over there, I couldn't find my giant size models so that everyone can see, but go ahead and grab the first pink ball over there. That's supposed to represent an s orbital.
You want me to
Actually, just pass it down the row if you want. You guys can take a look at it or not. I'll have these out, and when Lisa gets in this morning, I'll have her find my big models. I looked around last night for about half hour and couldn't find it, so it must be buried in some box that hopefully she knows where it is. But really, it really is just a three-dimensional sphere like that. So we've got s orbitals. We've got, for L equals 1, those are our p orbitals. Get my letters right. This is where it gets a little weird. P orbitals look like dumbbells. And depending upon who draws them, they can look elongated like this, or sometimes they draw them big and fat like that. And so p orbitals are what I just called dumbbells. And here's where, you know, the quantum mechanics, if you run through it, you realize that, you know, just from the Bohr model where everything is circular, that doesn't do much good for us, right? Or that, I mean, that's good. And then what happens is quantum mechanics, and because they're waves, we can actually start to get all of these funky mathematical shapes like these dumbbells. And we're going to find that the next set of orbitals are more complicated. Then the last set, I won't even attempt to sketch them. I would never ask you to sketch them, but you know, I might ask you to draw a dumbbell. I think most of our drawing skills are that good. Cody?
So like for labeling,
Oh,
would it be like?
we could call that a 2p.
Okay.
There is no such thing as 1p because if you go back, notice that for the first quantum number, you're only allowed to have s orbitals. It's not until you get to the second quantum number that you're allowed p orbital. So we can't have a 1p orbital, we can only have a 2p orbital. And then I guess since I was drawing size scales, you know, so here's, if this is my 2p orbital, then the 3p orbitals are just bigger. And again, remember, that's our n quantum number. This is simply saying that L equals 1. So we've got, you know, that seriously weird progression of numbers and then how they all fill out. So we can have 2p orbitals, we can have 3p orbitals, we can't have 1p orbitals. And here's the kicker. When we get to the picture of the periodic table and how it's built based on this quantum mechanics, you'll understand why we don't have a 1p orbital. Or you'll start to understand why the periodic table has its kind of funky shape. So the next quantum number would be L equals 2. That we said describes d orbitals. This is still the second quantum number. So this is details about the second quantum number. Remember, it's talking about the shape of orbitals. So for d orbitals, they tend to either look like 4 lobes like this. So I say they kind of look like clover leaves, or at least the good lucky kind. And you know, sometimes they'll draw them long and skinny like this. Sometimes they'll draw them super fat like that. But realize that all of those are the same. These could all describe, for instance, a 3d orbital. And so recognize that all those pictures are the same, right? There is one weird exception. One of the orbitals looks like this, where it's only got 2 lobes, and then it's got a weird funky ring around the side like that. And that's where the mathematics gets funky. I mean, seriously, you can't really understand this stuff until you run the numbers through the equation, and then when you know, have a big computer solve it, it spits out these funky shapes. So, for instance, if we come over here and take a look at the models by J, you know, here's my p orbital, right? So it looks like just a dumbbell. And then my d orbitals, most of them look like this. One of them has that funky shape where it looks kind of like a p orbital, but it's got like this disc around it. And, you know, unless you actually do the math, there's really no way you can possibly explain why there's that one exception. I mean, there kind of is. When we get to the next quantum number, we'll talk about it. Now, we said that L equals 3 is f orbitals. Do not attempt to draw these. They are ugly. So on the handouts I give you, and certainly if you go in your book, I think they show you some f orbitals. So here you can see on the overhead the pictures. Here's our, a 1s orbital. It's just a sphere. They show the 2s orbital, and if you kind of look inside, you can see the big one on the outside and the tinier one on the inside, right? Same thing with the p orbitals. Notice that there's a bunch of different ones that are oriented differently. We'll talk about those. Notice that we've got our d orbitals here that have those 4 lobes, and there's that funky one. And god darn it, this picture does not show the f orbitals. Are you kidding me? Because there's no way I'm going to draw them. They usually have 6 or 8 lobes, and they're just darn near impossible to draw meaningfully. Maybe if I click on this link, let's see. Add to favorites. What if I just want to open it up? Will it not let me do that?
Yeah, bathroom working either?
Are the bathrooms working? As far as I know, yes. Let's see, if we go to our favorites. Where's my bookmark thingies? Show bookmarks bar. What? There is none there? Oh darn it. Let's do this. I want to copy that somehow. Never mind. We'll go there later maybe. No, I'll just continue on with my lecture. Oh, that's a good idea. So, f orbitals. That's what I love about computers and Google. We'll just pop up some f orbitals. Like I said, don't try to draw them. Realize that they get ugly. So there's the f orbitals. Notice that, if you take a look at them, they've got 6 lobes in some, and that the the one that's the oddball, actually has 2 rings around it, kind of almost like a little planet. Sometimes I think about it. So realize that the f orbitals are ugly. No one wants to talk about them. We always ignore them. And we'll continue to do that in this class. Heck, even Chem 111 doesn't bother trying to talk about the f orbitals. They're just ugly. Okay, so that's the first and second quantum number. First quantum number is telling us how far out the electron is or how big the orbital is. Second one is just giving us those funky shapes, S, P, D, and F, right? The third one is called the magnetic quantum number.
How does it describe the electron?
Well, what it's saying is that the electron is not in spherical orbitals, or is not in orbitals like we would picture orbits around a planet, that they're more complicated than simply spheres. And so what it's telling us is sort of where the electron is, whether it's close to the nucleus, further out from the nucleus. We kind of knew that from the Bohr model anyway. And then the shape of the orbitals is what's going to lead us into determining the shapes of what molecules really look like. They're not just balls stuck together, right? Because they're not just s orbitals. They've got those p orbitals that have different shapes. They've got those d orbitals. We'll look at the shapes for molecules that have just s and p orbitals. We'll ignore the shapes for d orbitals. And so what this will transition into in Chapter 11 is looking at literally the shapes of atoms, or shapes of molecules, I should say, not the atoms themselves. So we've got our magnetic quantum number. It's given the symbol m sub l. So the idea is the little subscript L is simply telling us that it depends on the L value. And it can have values from 0 plus or minus 1, plus or minus 2, all the way up to plus or minus L. So notice that this quantum number depends on the previous quantum number, right? And what this really describes is the orientation in space of the orbital. And that also gives us the number of orbitals of each type. So we can kind of put those together as sort of being what it's talking about. So the idea is that if L equals, well, if n equals 1, well, actually, let's do it this way. If L equals 0, then that describes an s orbital, right? And the allowed values for m sub l are just 0. So that means that there's only one s orbital. If we take a look at what happens when we have L equals 1, that's describing our p orbital, orbitals. Now here, m sub l can have a bunch of different values. It can be 0, plus 1, or minus 1. And so that describes 3 different p orbitals. And what that's really describing is their orientation in space. So here's Jay's, this is as good as it gets for Jay's drawing skills. So here's my 3-dimensional axes. You know, here's my x, my y, and my z axis. And what it's saying is that one set of orbitals is along the x-axis. So we can call those px. It's saying that I've got another set that's oriented along the y-axis, so it's basically perpendicular to it. We can call those py orbitals. And it's got one last set of orbitals that's along that z-axis, so that's what we call a pz orbital. And so if you're kind of looking at these models, I mean, individually, they all kind of look the same. What we have to realize is that, you know, one is kind of parallel to the board, one is coming into and out of the board, and then the last one is going up and down. And so they really do have different orientations. And the kind of neat thing about it is if you take the sum of all 3 sets of orbitals, they almost look like a sphere too, mathematically. Not quite, but almost. And so the total set of p orbitals themselves are kind of spherical-like too. And so there's 3 different sets of orbitals. They have 3 different orientations around the atom. And so that means there's a total of 3 different p orbitals we can have. Now I label them px, py, and pz. After this, we probably won't bother talking about which orientation they're in because we don't care in this class. We just care if an electron is in a p orbital. We don't care if it's in the px, py, pz. And in fact, it's pretty hard to tell which set of orbitals it's in.
Wait, don't move on.
Now, that's the extent of Jay's drawing skill. That's the best looking picture you're going to get out of me all day, because I'm not even going to try to draw this with d orbitals. So this is all kind of weird, isn't it? Realize that at the tail end, hopefully we'll get there today, and we might skip just a tiny little bit and, you know, try to get you the big picture and then fill in a few details on Wednesday when we get to it, since we're kind of moving a little slow.
So, in that little model right there,
Yeah?
is there not supposed to be an s orbital on the s orbital?
Well, I didn't draw the s orbital because all an s orbital is a sphere, right?
Oh, okay, so these are just 2 different examples.
Right, right. So the idea is that I can have s orbitals, there's only one of them always, because there's only one orientation for a sphere, right? You can't have more than one orientation. But for those dumbbells, they can be oriented in space in different directions. So the next quantum number up is, oops, I don't want green, I like blue. Not the next quantum number, I'm sorry, the next orientations is if I have L equals 2, we said that described our d orbitals. And so m sub L then is allowed to have the value 0, plus 1, minus 1, plus 2, and minus 2, because it can go all the way up to L, right? And it starts at 0. And so that means that there's 5 d orbitals, or that there's basically 5 different orientations. And so if you take a look, for instance, at my models over here, and I admit I got the little ones, so it kind of sucks. That and I don't have my big lecture bench. What we're kind of saying is that, you know, I've got one set that's, say, flat in that plane, but then I've got another set that's, you know, at the same spot in space, sort of at a different orientation. And then I can also take and I can turn that one 45 degrees, so I get something like that, and I can have that one like that, and then that one like, you know. So there's all sorts of different orientations, kind of like those p orbitals, except for the d orbitals, there's 5 of them. And mathematically, the way the quantum numbers work is it gives us 5 different orientations. And again, I don't think I could draw the 4-lobed figures with different orientations. The last one we'll talk about just for completeness sake is L equals 3. We said that's our f orbitals. And so we can have m sub L equals 0, plus or minus 1, plus or minus 2, and plus or minus 3. So that gives us 7 f orbitals. So that kind of makes sense? Well, 1, 2, 3, 4, 5, 6, 7. So the number of different m sub L values that are allowed is also the number of different orientations. And so what that means is that there's 7 different orientations too. Meaning you can get those big ugly pictures and then now you can orient them in 7 different directions. And if we take a look at that other slideshow, assuming I can pick it out, notice that that's what it's kind of trying to show in these pictures, in that, you know, notice that this one's along that axis, this one's along that axis, that one's up and down, meaning they're showing different orientations of those orbitals. Okay, so we've got one last quantum number to worry about. That is the electron spin quantum number. This one is honestly the easiest to do. It's the hardest to conceptualize. It's given the symbol m sub s, and it simply says that m sub s is allowed to be plus 1/2 or minus 1/2. And so it only has one of 2 values, so it's pretty easy. It doesn't depend on any of the previous values, so it's always just plus 1/2 or minus 1/2. But what it describes technically is the direction. Well, okay, I'm going to even simplify it further. It describes the direction of the magnetic field of the electron. And what it turns out is that there's 2 ways you can think about it. You can think about an electron as having a north-south pole. Or you can think about it as the electron either spins clockwise or counterclockwise. And that gives a direction to the spin. Just like Earth has a north and a south pole because of the way it's spinning, well, because it's spinning, I guess, technically, not because of the way it's spinning, we can do that. And so what we generally represent m sub s as is either an up arrow or a down arrow. And what it really represents is how that electron spins around. Now, like I said, we don't really care about that. What we only care about is that it has 2 values allowed. And after that, we don't really care. And what it's responsible for is that if you take an atom, or if you take an element, and you pass it through a magnetic field, half of it goes up, is deflected up, and half of it is deflected down because of that electron spin. So there's our plus 1/2 and our minus 1/2 spin. And that's how they basically discovered it. What it really means is that all those little lines that we saw in those line spectra are really actually 2 tiny lines very, very, very close together, and that if you have enough resolution, if you can see clearly enough, then you'd be able to figure it out. Okay. I should also point out that there's lovely, like the pictorial write-up has all these pictures in it too. So I'm not really drawing anything. No, I'm talking about, I handed this out with the lecture notes a while back, didn't I? I handed it out with the homework last week before the test, even if I remember right, or on Monday of last week or something. So all of the pictures I'm drawing in here kind of are in this. It's a good study guide in that it really does summarize just about everything you need to know. It took me weeks and weeks and weeks to craft it, but it was well worth it. I shouldn't say weeks and weeks. It took me a while. Okay, so let's take a look sort of at a bigger picture then. So if I have a row for n, a row for L, a row for m sub L, and a table where I've got m sub S, then what I can do is I can build a model of the atom, or at least a model of where the electrons can be found. Now, some of these values are pretty easy, because what's m sub S always? Yeah, it's plus or minus a half, right? So I can even go in and fill that column in and just, draw a big old line going down. And what this really means is that each orbital can hold 2 electrons, because I can have plus 1/2 minus 1/2. The other way I like to think about this picture is, remember this is describing where electrons are, right? Well, we can use the same analogy of where people live. For instance, we can consider N to be what block you're on. And we might consider L to be what apartment complex you're in. And M sub L could be what floor your apartment is in. And then every apartment is a 2-bedroom, so you can put 2 people in it. And so we can, as an analogy, you can think about the fact that electrons, kind of like people, can't occupy the exact same space. And so each person is going to have a unique address that they live at. And you could address, say, their mail to them by simply having a unique set of quantum numbers. It's actually technically called the Pauli exclusion principle, which simply says that no 2 electrons in an atom can have the same 4 quantum numbers. Just like saying 2 people on the planet can't occupy the exact same space. Now,
Will you say that one more time? I'm sorry.
I'll write it down on another slide here. So Pauli, we'll come back to it anyway. Exclusion principle. And that is no 2 electrons can have the same 4 quantum numbers. Or what it's really saying is that electrons can't exist in the same space. Just like 2 people can't live in the same space. Now, admittedly, the analogy breaks down. Can you have 2 people living in the same, more than 2 people living in an apartment? Sure. Heck, you can cram in like 30 Mexicans. Whoops, I said that on tape. You guys can go get me fired if you want for being a racist pig. And things like that. But, so realize that the analogy to housing is not perfect, but it's reasonable. So if we go back and start filling out this table, what we realize is that because of the way the quantum numbers work, sure. Remember, all of these videos are posted, so if you ever miss something or want to review, or really if you're having trouble sleeping at night, just pop this up on your computer screen and my voice will drone you to sleep.
Go ahead.
It really does. So if n equals 1, L is only allowed to be 0, m sub L is only allowed to be 0, and we're going to call this our 1s orbital. Because remember, 1 is the principal quantum number. This is our n. This is our L. We don't talk about or usually put our m sub L orbital in there, or the number for it, because honestly, we don't keep track of which one it is anyway. So then we can have 2, 0, 0, plus or minus a half. And that's our 2s orbital. And so remember, there's 2 electrons that live there. There's 2 electrons that can live in those orbitals, because we can have the plus or minus a half for the m sub s.
Is plus minus half goes for the second two?
I'm sorry, what?
Is plus minus half goes for the second two?
It goes all the way down to the bottom of the page. That's why I drew an arrow. Like I said, that's the easy one, right? We can fill that in before we even think about anything. But for quantum number 2, we can also have L equals 1, and then we, oops, I wrote L instead of 1. L equals 1, and then remember, m sub L can be 0, plus or minus 1. We're going to call those our 2p orbitals. And we can fit a total of 6 electrons in those, because what we're really saying is that I can have 2, 1, 0, a half. I can have 2, 1, 0, minus a half. I can have 2, 1, 1, 0, a half. Oops. I can have 2, 1, minus 1, a half. And then, of course, I can have the negative counterparts to that. Oops, that's got to be a 1. And so I really can put 6 electrons in that 2p orbital, because I've got 3 different orbitals, and each of those 3 different orbitals can hold 2 electrons. So 2 times 3 is... I'm going to keep the math as simple as possible. In fact, if you can do multiply by 2, you're pretty good.
You said, how'd you get 2, or how'd you get 3? You said 2 times 3.
Okay, so m sub l can have 3 different values here. So that means there's 3 orbitals times 2 electrons each, for a total of 6 electrons in that orbital.
And then 2 electrons each is from
From the m sub s value. So remember, m sub s can be plus or minus a half. So notice in my example down here, these are the only numbers that are changing. The first 2 sets of numbers that are describing the distance out and the shape of the orbital don't change. What changes is the orientation and, of course, the m sub s value. What? Okay, so that's our second orbital. Now, I'm going to have to redraw this chart. N, L, m sub l, m sub s. We said this is plus or minus 1/2. So I can start with 3. So I can have 3, 0, 0. Oops, I guess I can move that up so it's in the same line. 3, 0, 0. So this is describing our 3s orbital. Then I can have 3, 1, 0, plus or minus 1. That's describing my 3p orbital. So I can put 2 electrons, 6 electrons. And then, see, with the 3 orbital, now I can have the d orbitals. And that has plus or minus 1 and plus or minus 2. So that means that there's the 3 d orbitals. And there's 5 of those times 2 electrons for a total of 10 electrons in a d orbital. Don't worry, the kicker's coming. We'll finish up in the next 8 minutes. And again, I got to be honest, read the book, look through the sheets, work through the homework. What you'll find is that, yeah, at first glance, this is just weird and doesn't make sense. But as you start to pick up on the patterns, as you play around with the little math rules, if you work with it, everyone gets that aha moment. I've never had anyone not have at least a semi-aha moment. There could be a first. I always leave that option open. So that's my s orbital, or my 3 orbitals. Now for 4, there's a lot of repeat, right? Meaning I shouldn't, you know, the 4, 0, 0, the 4, 0, 0, plus or minus 1, and 4, oops, 1, 2, 0, plus or minus 1, plus or minus 2. That's just our 4s, our 4p, and our 4d orbitals. Do you notice the pattern starting to repeat itself? We just had 1s. Then for the second orbital, we had 2s and 2p. Then we had 3s, 3p, 3d. Now we've got 4s, 4p, 4d. And then, of course, what's the last one? If I have my f orbitals, this is my 4f. And what that means is that there's 7 orientations, so there's 7 orbitals, times 2 electrons means I can fit 14 electrons in an f orbital. So as the orbitals get bigger, I can fit more and more electrons around an atom. That kind of makes sense. Because remember, electrons repel each other, right? So when they're really close to the nucleus, they're going to repel each other, and you can't put many in. The further we get from the nucleus, the more room there is to do it, and the better. So think about an s orbital is a 2-bedroom apartment, a p orbital is a 6-bedroom apartment, d orbitals are 10-bedroom apartments, and f orbitals are the 14 bedroom apartments for the Mexicans.
I just, rewrite.
Or arguably, we could say the Mormons, they like to have lots of kids too. And I can offend more people since I don't have any Mexicans in here, but I have lots of Mormons in here. Are you guys truly offended? My theory on making offensive statements is if, as long as everyone knows I'm not serious about any of it, then we're okay. And if anyone actually ever thinks I'm serious, they're screwed in the head and they don't really pay attention in class. Because I'm probably the least serious person I can think of for that. Now, you go to my friend's grandma when she was, man, when we were kids growing up, we'd go over to grandma's place. She was one racist old bitch. Man, I'm serious, like, you know.
My grandma was pretty racist.
Yeah, I mean, my grandma didn't seem to care one way or the other. She would always be making comments about, you know, and damn N-words and Mexicans and
My grandma wasn't
everything.
She was ignorant. She grew up in Missouri, southern Missouri,
Well,
so she didn't know any better. Like, the whole world stopped
Yeah.
in 1950 to her, you know.
That's kind of the way my friend's grandma was, but it was hilarious to listen to her talk. As long as you just took her with a grain of salt and said, that's just so wrong in so many ways.
We just wanted to take my grandma anymore. She made comments constantly.
Okay, so how does this relate to the periodic table? This is where, to me, things get interesting. And we're skipping a tiny little bit to get to this picture just so you can have it in your head, and then we'll come back and we'll talk about the exact way it's done. So notice that the way my orbitals are filled, I first had my 1s orbital, right? And we said s orbitals can hold 2 electrons, right? Well, what are the elements that have 2 electrons? Well, not 2 electrons, but we have hydrogen and then helium, right? Now, we'll talk about why helium is sometimes put over here when helium really could go here in the periodic table later. Now, I've always said hydrogen is the exception to the rule. Helium's, but why is it considered a noble gas? Why isn't it fit, you know, the way the orbitals go? We'll talk about that. That's one of those little things that it's like, okay, this is a little trick, or it's the exception to the rule. So notice that we had our 1s orbital first, right? And then, so this represented our n equals 1 quantum number. So that whole first row is n equals 1, right? And then our second row down is n equals 2. Well, for that, we had our 2s orbital, right? And then we had our 2p orbital. And then notice that, you know, for our 2s orbital, it's got 2 places for electrons. Our p orbital said we have 1, 2, 3, 4, 5, 6 electrons we can put in it, right? Notice that this whole block over here is sometimes called the p block elements simply because all their electrons are in p orbitals, right? And notice that then for n equals 3, we have our 3s orbital we talked about. We have our 3p orbital. And here's where it gets a little weird again, and we'll talk about the exact why of this. This is the part I'm skipping because we're running a little short on time. We have our 3d orbital, right? How many electrons could we put in a 3d orbital?
10.
Yeah, so this is 10 electrons wide. If you count the d block in your periodic table, it's 10 elements wide, right? We'll talk about why it's shifted down one row after Wednesday, okay?
Are you going to print that out?
Am I going to what? Print? Yes, I'm going to print those out. And also, please notice, I also said most of these pictures are right here in that handout that I've already printed out. They're just tinier. But you can, if you want, that's on the website. Go ahead and print this out, cut and paste these, and stick them straight in your notebook if you want. Or, you know, I've also printed them out on that study guide. So there's our d orbitals. And then we talked about the f orbitals. How many electrons fit in an f orbital? How big is that block if you pull out your periodic table and count across it? 14. Now remember that this really is stuck right here. Meaning, if I was really to draw a periodic table, I should have s orbitals, kind of like, you know, meaning that that's supposed to be physically stuck in that spot on the periodic table, right? It's just that we draw it down below, because otherwise the periodic table doesn't fit on a piece of paper. Meaning a periodic table really should look like, I'm not going to get the right one, am I? Oh, should really look like this. You know, we should have our s orbitals, and then way down here is our f orbitals, and then here's the d orbitals, and then there's our p orbital. So this is really s, f, d, p. But what we do is we say, screw that, it doesn't fit on a piece of paper. Let's take our s orbitals, or our f orbitals, and stick the f orbitals down here. So we really have, you know, s, p, d, and f. But remember, the f are really sandwiched in between there, way down on the bottom of the chart. And in fact, some charts show that a lot better. They'll actually leave a space for them there, kind of. Some charts just make the assumption that you know that, and since you're a chemistry student, you're wise to that. So recognize that the shape of the periodic table is solely determined by those 4 quantum numbers. And that's one of the things that, like, for instance, Mendeleev, or however you want to pronounce it. Is that pretty good? Mendeleev? Mendeleev. Mendeleev. I'm not going to remember this next year, unfortunately. I really should maybe take a course in Russian. Anyway, you know, he figured out that all the elements in a column line up for things that react kind of the same, right? And it wasn't until quantum mechanics that they could say, okay, this is why they're lining up in columns. It's because their electrons are in the same type of orbitals, just further out, depending, you know, the further you go down the table. And, you know, it explains the size of the s, the d, the p, and the f blocks in a normal periodic table, and realized that the periodic table was built primarily before quantum mechanics. So the fact that quantum mechanics just magically, to me, certain, you know, because of the way the math works out, spits out the shape of the periodic table, I gotta kind of tend to believe in it. That was one of those aha moments that I had where it was like, wow, it like really, you know, the whole periodic table is built around quantum mechanics. And they didn't know that quantum mechanics, when they worked out the math of it, was going to produce the periodic table. It just so happens that it did. And to me, that's one of those things where it's like, wow, it can independently produce something that I already believe in. I'll probably think that quantum mechanics is at least believable, or at least it's usable. So I don't know where we are in all the homeworks. Certainly, if we take a look at like what we're doing for the week, I'm pretty sure you can do A and B. Let's see, 10B. What's 10C look like? I'm pretty sure you can do 10C. Oh, no, you can't. Never mind. You can do little bits of it, but not quite. So definitely 10A and 10B. Oops. Let me see, where's 10B? That's what we're getting to. I just have to refresh my mind which one is which. Because the other class has similar homework to this. It's just that they also happen to have, come on.
You can only do a couple on 10B.
I was going to say, I think you should be able to do the whole thing, unless it's
10B or 10B?
B.
I think you can
B as in boy. Yeah, that's just literally reproducing the notes and answering a few questions at the end. So let's say that 10A and B are due Wednesday. Obviously in lab, we're going to cover the pre-lab is due. If you have questions on the pre-lab, bring them to my office hour. Otherwise, if you read the lab carefully, I think you'll find that the pre-lab and the lab are doable. The graphing part, you know, make me a pretty looking graph. The data is in there. The graphs that you have to make are simply the graphs that are actually in the lab. You just have to put forth enough effort to figure out what's being plotted on the X and Y axis and then figure out how to make it look pretty in Excel. I got to be honest, I think the hardest part is probably trying to figure out how to make it look pretty in Excel. Due tomorrow.